Welcome to the Michigan Energy Code training presentation. My name is Bill Bazdeck. I'm a professional engineer. This project is supported under a grant from the Department of Energy to the state of Michigan. It's being administered by the Michigan State Housing Development Authority. The production is by Michigan State University. The project objectives are to increase understanding, improve compliance, reduce administrative time, and improve customer relationships between all those individuals involved in the building trades. This is the summary of our presentation today. We're going to talk about why we need energy codes, the present status, the relationship between the International Energy Conservation Code and the Michigan Uniform Energy Code, some compliance tools by which we can assure compliance with the code, one of which is ResCheck, and we'll talk about some additional things. The reason we're talking about energy codes today is because energy is such a large portion of our life in the United States. The energy used by buildings, according to a recent survey by the DOE, is almost 40% of all energy consumed in the U.S. And we have an opportunity to impact that. We are involved in the building trades. We construct buildings, we remodel them, we maintain them. And so we are indirectly responsible for a great portion of the energy that's consumed in the U.S. The Energy Code for residential construction primarily focuses on the building envelope. There's quite a bit of mechanical in there, very little surface water heating, very little lighting, and some electrical power. Primarily, again, the focus is on the structural cocoon that encloses us, the walls, the windows, the roof, and the skylights. A reference for much of the information you will see today is the website energycodes.gov. I encourage you to record this reference, put it on your browser in one of your favorite locations. You will go here a great deal. This is a wealth of information. And many of the slides that you will see today came from sources from this website. The current status of the Michigan Energy Codes is as of March the 9th, 2011, the new code cycle began, incorporating the new building code. Here is the residential building code, the electrical code, the plumbing code, the mechanical code, and the energy code. This is the National Energy Code. Michigan has modified it with amendments to become the Michigan Uniform Energy Code. And this is the subject of our discussion today. The status of the energy codes in the various states throughout the United States is shown on the website from the Building Codes Assistance Project. And as you'll see, the colors represent the status of the codes. And Michigan, with the darkest color, is contemporaneous with the most recent code. It meets or exceeds the 2009 IECC or equivalent. There's a similar map for the commercial energy codes. And as you see, Michigan is also contemporaneous with the most recent code, the 90.1 ASHRAE standard 2007. And again, as of March the 9th, 2011, we have adopted the entire family of codes, the International Energy Code, but modified by the state of Michigan for use within our jurisdiction. And here they are both shown. The International Code, the ASHRAE Standard 90 for the commercial, and the Michigan Uniform Energy Code, which covers both of them. We'll get into the details of how that happens. The amendments to the National Code are Part 10 from the Department of Energy, Labor, and Economic Growth. Part 10A is the Commercial Code. We're going to cover the prescriptive approach in this session today, which acquaints you with the language of the codes and the various tables in which the requirements are outlined. This prescriptive approach requires no computer program with which to comply. It is simply do it like it's printed and you comply with the code. However, many buildings cannot meet the prescriptive code for one reason or another. They have features that are outside the limits of the tables, exceed the values, and they must go to a different means of demonstrating compliance. And there are other methods, computer programs particularly, which do that. But for the purpose of the training today, we're going to concentrate on the prescriptive, do it like it's written approach. The International Energy Conservation Code is available as a PDF file at reduced cost from the International Codes Council, or you can purchase directly the Michigan Uniform Energy Code from the state of Michigan. The relationship between the IRC and the IECC is that the IRC is the entire residential building code. It incorporates all of the codes, the mechanical, electrical, and plumbing codes, and the energy code. The IRC has a Chapter 11, which is also energy code. But Michigan has modified the IRC to the Michigan Residential Code, and in so doing has deleted the Chapter 11. It has replaced it with the IECC, the International Energy Conservation Code, and Michigan has adopted this with amendments, and they have made it in turn the Michigan Uniform Energy Code. The changes from the previous energy code are that there used to be a trade-off allowed for a high-efficiency furnace to compensate for an otherwise non-complying building envelope. That trade-off is no longer allowed. There was an abbreviated table in here, very easy to fill out with a pencil. That table is gone. In previous energy codes, there were allowances for high-efficiency furnaces, which could be used as trade-offs to compensate for otherwise non-conforming building envelopes. In other words, an R value that was substandard in the walls or the roof, at the end of the calculation could be compensated for by installing a condensing furnace. That is no longer allowed. That calculation table in the previous energy code is no longer allowed either. We don't have that abbreviated form that you filled out with a pencil. A new requirement is that at least half of the lamps installed in permanently installed light fixtures be of the high efficacy type, and that's an unusual word. We'll talk about that later. It's defined up in Chapter 2. The R value requirements for walls and ceilings are almost the same as in the previous code, slight modifications. What has changed, however, is sealing up the house to reduce infiltration. The new code adds a great deal of rigor to air barriers, to caulking sealing, and vapor barriers, and it adds additional inspections to ensure compliance with these more rigorous requirements. There are other methods of complying with the MUEC that are not specifically mentioned in the code. Their programs are such as HERS, the Home Energy Rating System, or the Energy Star program. The Michigan amendments to the MUEC are primarily administrative in nature. They changed the name of the code from the International Energy Conservation Code to the Michigan Uniform Energy Code. They also eliminate any references to climate zones that do not occur in the state of Michigan, and all of the tables are modified accordingly. They also drop any requirement for solar heat gain coefficients for windows in the state of Michigan. There are some other changes, such as type IC, or insulated ceiling rated CAN light fixtures installed in insulated ceilings. The use of energy trusses, or what are called raised heel trusses, are addressed in the code, and also re-roofing under certain circumstances. To demonstrate compliance with the code, we're primarily going to talk about the prescriptive method today, and that's to give you an understanding of the wording of the code and the U values and R values in the various tables. If you cannot comply with the prescriptive method, if for some reason your house is built in a way in which some element cannot meet the prescriptive code, then there are other methods of complying. And they are to demonstrate performance by means of a computer calculation program. One of the programs is written by the federal government, Department of Energy. It's called ResCheck. It's provided free of charge. You can download it from their website. There are other programs written by other agencies, other companies, such as the REM-Rate program, which calculates the thermal performance of the building over an entire year. So it actually incorporates the cost of energy and compares your proposed building with a standard building. We're not going to talk about those today. So again, if you're able to use the prescriptive method and all of the elements in your building are able to comply with the printed information in the various tables, you don't have to have any kind of a computer program. If you cannot do that, the ResCheck can provide a trade-off. ResCheck provides a U times A calculation alternative where you balance one building element against another. And if you choose, you can use another system such as REM-Rate or the eQuest program from the federal government, which is also free of charge. Another method of demonstrating compliance with the energy code is to use a third-party software, such as eQuest, which is available free from the Department of Energy, or a software program called REM-Rate. The structure of the new energy code is comprised of 6 chapters. Michigan has amended various parts in different chapters. In Chapter 1, they have changed the name of the code from the International Energy Conservation Code to the MUEC. The definitions are mostly untouched. There are a couple of changes. Chapter 3 are the climate zones, and this is different from the previous code in which we had climate bins. Chapter 4 is our residential energy code, about which we will be talking today. Chapter 5 is the commercial energy code, which references the ASHRAE Standard 90.1, version 2007. And Chapter 6, again, are some references. The residential code primarily focuses on the building envelope and the efficiencies of the thermal performance of walls, windows, and roof. The insulation levels and window U factors are specifically mentioned in the code, and again, we're particularly concerned about infiltration. The code talks about some mechanical things, and a new feature of the mechanical portion of the code is that we're going to have to be sealing up ductwork and insulating it where we never did before. Federal law covers the efficiency of appliances, heating appliances, cooling appliances, and sets those efficiencies outside this code. We do not refer to any heating and cooling or hot water appliance efficiencies. And the lighting equipment, again, at least half of the lamps have to be of the high efficacy type. And there's that word again that we'll talk about in just a minute. In the code, different types of spaces are defined, and the relationship between them and what levels of insulation must be between them. Between occupied heated spaces, conditioned spaces, semi-conditioned spaces, semi-heated, unconditioned spaces, and the levels of insulation that go between them. Here in this illustration on the left, you'll see an unheated garage right next to a family room. And so that wall, even though it's an interior wall, must be a fully insulated wall as if it were exposed to the outside. Under Chapter 1, we find out where the code applies to existing buildings, historic buildings, additions, alterations, renovations, changes in use. Let's say we're finishing an otherwise unfinished space that might have been used for storage. We're turning it into a bedroom or a recreation room or a den. And so the code now applies when you change the use of a space. And if we're going to have an unconditioned space, suddenly we're going to heat it or cool it, now the code begins to apply again. In Chapter 1, however, some of the exceptions are the most interesting things. For instance, storm windows over existing windows do not have to comply with provisions of the new code. And baseball throw window, a broken glass, you can replace the sash with one of like kind. You don't have to go to a new, highly efficient window. And if you're remodeling and you're exposing a wall cavity or a ceiling cavity and you find it's already full of insulation, the code says you do not need to bring it up to the current values. For instance, you might have a 2x4 stud wall that has R11 insulation in it, installed back in the 60s. The current code says that you have to have R20 in the walls. It says you do not have to bring the insulation up to current levels if it's already filled with insulation. And it says it doesn't make you go exploring. If you're not opening up a wall or a roof, it does not force you to go looking to see if there's any insulation in there at all. However, when you're re-roofing, you have to see whether the existing roof has insulation. And it says where neither the sheathing nor the insulation is exposed, if you're doing a second layer of shingles over the first, you don't have to worry about it. But if you do expose the ceiling cavity and you find out there's no insulation in there, then you have to bring up the entire roof to current energy code standards. There are some more exceptions. Very low energy use buildings. Buildings that are not heated or cooled or heated only to 3.4 BTUs per hour per square foot need not comply with the code. Well, that's an odd number. Where did that come from? Well, that's the conversion between watts and BTUs. That means 1 watt per square foot. And an existing building, if you're not touching the building, but you're going into the building and replacing furnaces or air conditioners, which is more frequent, you're going to do that every 15 to 20 years, you don't need to bring the building up to compliance with the envelope requirements, but you do have to install new appliances, heating and cooling appliances, that comply with the Federal Energy Code minimum efficiency standards. 80% for furnaces, 13 SEER for air conditioners, and 0.62 energy factor for water heaters. And buildings that are on the National Register of Historic Places do not need to comply. However, there are some local jurisdictions that have historic districts in which they wish to maintain the appearance of the old buildings as they were built 200 years ago. And there may be local codes which supersede this, where you might go in there and do some alterations and want to insulate the space, insulate the roof, whatever, put new windows, new highly energy efficient windows in, but the local codes say no, you cannot do that. This is up to the local authority having jurisdiction. They want to maintain the buildings with the appearance they had when they were originally constructed. Mixed-use occupancies are something that you will encounter quite frequently in old downtown areas, where on the first floor of a multi-story building you'll have a commercial shop, but above it on the second and third floors you will have residential space. The code says that you treat the commercial space under the commercial code and the residential space under the residential code. Now, the code is not intended to limit your creativity in using new items, new materials, or new concepts. The code is suggestive of the way that you shall insulate the building to provide an overall thermal performance. If you wish to use a new concept, talk with your local authority having jurisdiction. Your local code official will work with you, so go to him first before you begin the project. The information submitted with the building permit application has to be a lot more extensive than in past code cycles. Now we have to supply to the building plan reviewer such information as the materials that we're going to use to insulate the building and what the U values shall be. The window U values in fenestration is windows, doors, and skylights. So windows, doors, and skylight U factors, the area weighted U factors of windows, the design criteria for your heating and cooling systems, the design criteria for the water heaters. What types of water heaters and what efficiency are you going to put in? How are you going to seal up the ductwork? What methods are you going to use to seal up the supply and return ductwork? Has never been requested before. What kind of insulation you're going to put on the ductwork and the piping. A lighting fixture schedule with a wattage and controls. It used to be you'd simply give your homeowner an allowance and say, here's $10,000. Go to the local lighting store and select your fixtures. Well, now you can do that, but it says that on the drawings or the submittal documents, you must have a lighting fixture schedule. And in that schedule, you must show that at least half of the lamps in the light fixtures have to be of the high efficacy type. And the homeowner can still go buy whatever type of fixtures they wish, but they must select them according to the type of lamp that's in the fixture. We have to submit the details of how we're going to seal up the house, where we never did before. We're going to be showing them where we're going to caulk, what type of materials we're going to use, what material we're going to use for the vapor and infiltration barrier, and all these details have to be on the submittal documents, the original submittal for your building permit. Now, Chapter 1 Administration, we talk about many of the standard things that we refer to as boilerplate. The inspections, the validity, the reference standards, fees, which have been amended by the state of Michigan, stop work orders, and how you appeal any adverse decisions. The definitions are largely untouched in Chapter 2. There are a couple of changes. The definition of building and code or building official has been changed, and they changed the definition of building to exclude agricultural structures which are not used for retail businesses. The federal government has changed the climate zones throughout all federal documents to a system of 8 climate zones now, the warmest climate zone being in southern Florida and the Keys, and the coldest one being up in Alaska. Zones 1, 2, 3, and 4 are outside the state of Michigan, as is Climate Zone 8. So all references to those climate zones in all of the tables in the Michigan Uniform Energy Code have been deleted. You'll see that we're in Climate Zones 5A, 6A, and 7. Well, what does that mean? From east to west, you'll see that in addition to numbers, we have A, B, and C. The eastern half of the United States is called a moist climate, where moisture comes up from the Gulf of Mexico. That's Climate Zone A. And the central portion of the states, the mountains and the plains are climate zone B, which is a dry climate, and marine climate C on the west coast. So you may have climate zones in all three, A, B, and C. For instance, climate zone 4 occurs in A, B, and C. Climate zone 5, one in Michigan, occurs in A and B, as does 6 and 7 as part of the Upper Peninsula. You'll notice that part of climate zone 6, which is in Wisconsin, intrudes itself up into the middle of our Upper Peninsula between two portions which are in climate zone 7. On the Michigan website, they have detailed the heating degree days for each of the three climate zones that occur in the state of Michigan, climate zones 5A, 6A, and 7. And they further zoomed in on the state on the website to show the counties in more detail. And there's the climate zone 6, which intrudes itself into the middle of the Upper Peninsula. Notice around Saginaw Bay, where instead of going north to get to a colder climate zone, you go west. And it has to be with some lake effect coming off Saginaw Bay, which makes the climate a little milder right there. On the Michigan website, they actually list the counties individually to help you see where your county falls in climate zones. And the Residential Energy Code now gives specific details of the temperatures around which you must design your heating and cooling load calculations and select your heating and cooling equipment. They say 75 degrees for cooling and 72 degrees for heating must be the basis of design. And further on in the code, it says that the heating contractor shall also leave the room thermostat set at these temperatures when finished with the project. Chapter 3 is climate zones, but on the last page of Chapter 3 occur some mandatory requirements where you might not otherwise look for them. They are the mandatory requirements for labeling of insulation. And basically, if you have a faced insulation with a craft or foil vapor barrier on them, you have a nice, clean surface on which to print all the data regarding that particular insulation. However, if you have a sprayed-in place, or a blown-in place, or a stay-fit batt insulation on which there is no surface to print this, you must have manufacturers' data sheets and applicators' data sheets to submit with your building permit application that show how this material installed in this manner, in this thickness, will yield this R value. And there's also a requirement for attics where you pour in a loose fill insulation, such as fiberglass or vermiculite, or even chopped cellulose, that you have depth gauges installed, at least one for every 300 square feet of the attic, which can show you how deep the insulation is. Now, you could use a yardstick, except for the fact that they require that the numbers on these gauges be at least 1 inch high, so that a person sticking their head up through the scuttle hole and looking out across the attic with a flashlight can easily read the depth. Now, it goes without saying that those gauges have to start at 0. You don't want to cut them off at 6 inches and fasten them to the side of a roof truss. And the inspector will probably dig down through the nearest insulation and see that that gauge does indeed start at 0. Again, the insulation has to be marked and the marks have to be displayed. And the R values of insulation must be demonstrated by tests conducted at 75 degrees because the insulation values change with temperature. All materials have insulation that changes with temperature, and so the test must be conducted at a temperature in which we live, our normal living environment. And again, the labels can easily be displayed on foil-faced or craft-faced paper insulation products, but the stay-fit batts require a certificate. The U-factors of fenestration materials, windows, doors, and skylights, have to be determined in accordance with tests meeting the NFRC standards. That's the National Fenestration Rating Council. They have standards 100, 200, 300, and 400, 100 referring to the thermal performance or the U values. And they're asking for a test conducted by an independent testing agency. The product data sheet shall not supply information that's supplied by only the manufacturer. They want somebody to verify that. If you cannot get such a certificate from an independent agency, then you're forced to go into the prescriptive tables to use a default value. And where the prescriptive table says that we want a 0.35 U value for a tested and certified window. If you cannot get the test, they say you must use a U value of 0.55, and that's a significant penalty for you. And in the most recent edition of the MUEC, Michigan has allowed an additional feature, which is a computer simulation of a laboratory test. This computer simulation has to be done by the same independent testing laboratory, but it's equivalent of having run that window through an environmental chamber. And the windows have to be installed in accordance with the manufacturer's recommendations, installing all of the flashing and sealing strips that they recommend. The residential code applies to the building classifications R2, R3, and R4 in buildings 1, 2, and 3-story high. Now the R is the residential classification. There's an R1 classification also. But the MUEC says that R1 is a commercial building. That's the hotel and motel. So even though people live there at night, they don't live there for extended periods of time, and it's a commercial operation for profit. So the R1 hotels and motels are commercial, as is all residential which exceeds 3 stories in height. So high-rise apartment buildings, 4 stories and up, are now examined under the Commercial Energy Code. Now we're in Chapter 4, which is the residential chapter. And the sections in Chapter 4 refer to the air leakage of the entire building, the maximum U values for windows and doors and skylights, the temperature controls for mechanical systems, how we're going to seal the supply and return air ductwork, how we're going to treat building cavities as regards to using them for supply or return air plenums. And these provisions in Chapter 4 are mandatory. You must comply with these whether you're using the prescriptive method directly from the tables in the code or whether you're using a computer simulation program as an alternate performance method. New in this code is the requirement for a certificate that you print and stick on the front of the electrical panel. This certificate is a list of all the features of this residence. What the R values of the walls, the ceilings, any thermal insulation in the building, what the U values of windows and doors is, what the sizes and efficiencies of the furnace, the air conditioner, and the water heater are, any information about possible freestanding heaters that are unvented, installed in semi-heated spaces, even though they have no efficiency rating. All this information has to be typed in legible form, dated, signed, laminated, and adhered to the front of the electrical panel with a permanent adhesive. And the reason is so that all future owners of the building down through the history of the building for the next 100 years or more will know how the building was originally constructed and insulated. The very first table in Chapter 4 summarizes all of the thermal performance requirements for all components of the building envelope. There are 3 climate zones shown, the ones that occur in Michigan, 5A, 6A, and 7. And for instance, in climate zone 5A, the most southern, the requirement is for a U factor for the fenestration, which is again doors, windows, and skylights, to be 0.35. This is the area weighted overall average U value for the windows. And to achieve that value of 0.35, you'll probably have to use a low E glass with an argon filling. That's available easily on the market. Skylights have to have a U value of 0.6. Insulated ceilings in the most southern climate zone, an R value of 38. The northern 2 climate zones, R value 49. Wood frame walls, R20. Insulation between the studs. Or you can have R13 between the studs if you wish to put a continuous R5 insulated sheathing over the outside. Mass walls, which are walls defined as those having a thermal flywheel effect, in other words, a long time to heat up and a long time to cool down, and they hold a great deal of heat. They have to have an R value of 13 or 17, and what it says that the second R value applies when more than half of the insulation is on the interior. Floors over unheated spaces have to have an R value of 30. Basements will have an exterior insulation on the outside underground of R10, or if you wish to put it on the inside between studs, an R value of 13. Slabs, slab on grade, which is quite unusual in building construction, residential building construction, except For a walkout basement, in which the outside edge would indeed be a slab on grade, they have to have an R value of 10 for a depth of 2 feet in the most southern climate zone, an R value of 10 down to 4 feet in the northern 2 climate zones. And the crawl spaces have to be insulated with either R10 on the outside or R13 on the inside, just like basements. Additions to buildings, and this is quite common, an addition is installed on an existing building, have to be permitted under the new residential code. They have to meet all the features of the code as we're talking about it today. However, we do not have to go back into the existing home and bring the home up to the current code. And for remodeling, there is no 51% rule in this code. In other words, only the portion of the building that you touch during remodeling must you bring up to the code. Untouched portions, unremodeled portions of an existing building stay as they are. Now, if you choose not to use only the insulation components, the second table in Chapter 4 talks about the U factor of this wall. And again, here's a table with all 3 climate zones and all the same features of the building envelope and the U values for these. And you can use these as an alternative in the prescriptive method of compliance to the pure insulation values which occur in the first table. Now the U value is the heat flowing outwards through a wall. And to calculate the U value, you take in all features of that wall, from the inside air surface to the inside wall material, which is typically half-inch drywall, to the combination of studs and insulation in the wall, to the sheathing on the outside, the siding over the sheathing, and then the exterior air surface. The R values of all those components are summed, and you divide them into 1, you take the reciprocal, and that's the U factor. And again, for windows, it's the same 0.35 as we saw before, the area weighted average. Skylight's the same 0.6. Ceiling U value, remember it was an R value of 38, now it's a U value of 0.030. And again, the walls, the mass walls, the floors, the basements, and the crawl spaces are also referenced in U values. You have the option of complying with the prescriptive method of the code and using either method, insulation only or total wall U values. And using the values from this second table, it's called the UA alternative, the U values times the area of the surfaces. And the calculations must be performed in accordance with methods determined by ASHRAE, and that's the American Society of Heating, Refrigerating, Air Conditioning Engineers. The ACA Manual J, the Air Conditioning and Contractors Association Manual J, is designed in accordance with these ASHRAE calculation methods. So again, we have 3 methods of demonstrating compliance. We have the prescriptive method using strictly the R values from the first table in Chapter 4. We have the prescriptive method using the UA alternatives from the second table in Chapter 4. Or Section 405 of the code allows what's called a simulated performance method of complying with the code. And this is a computer method. It's not a prescriptive method. Michigan has modified the international code to change the way in which raised heel trusses are treated in the state. The international code says that you can reduce the attic insulation in any residential structure if you install a truss which is called a raised heel or energy truss. And that basically allows the full thickness of attic insulation out over the top of the exterior wall. The international code says you can reduce the R49 requirement to R38 in the northern 2 climate zones of Michigan, and the R38 down to R30 in the southern climate zone. The Michigan has amended that to say no. In the southern climate zone, the minimum insulation value is R38, whether or not you choose to use an insulated or raised heel truss. In a standard truss, the insulation tapers down as it approaches the exterior wall. There's less insulation and more heat flow through this point. And this is what forms ice dams. Snow building on the roof in the Michigan climate is melted by heat flowing through this edge of the roof. And the water flows down under the snow to the unheated soffit and freezes. And over time in the winter, this repeats itself until the ice dam builds up and the water leaks under the shingles and leaks into the house and causes physical damage. The raised heel truss allows the full thickness of attic insulation to be installed out over the exterior wall. It does that by raising the top chord of the truss up to the value of the insulation, the thickness of the insulation. If you have fiberglass in the attic, that's R3 per inch, the R38 requirement. 38 divided by 3 is about 13 inches of fiberglass. So that little member, which raises the top chord, has to allow at least 13 inches plus an airspace over the top. Now, ceilings without attic spaces, where you cannot put R38 insulation up there, and there may be a number of different types of ceilings in the same house in which this is the case. A rafter ceiling in a cathedral ceiling, a rafter in a sloped or shed ceiling or a flat roof may not have the space to put R38 insulation in. The code allows up to 500 square feet of this ceiling to have a R30 insulation value. However, if you're using the alternative approach, you cannot do this. This is strictly the do-it-like-it's-printed prescriptive approach that allows this. The next section talks about attic access hatches. They say that the top side of the hatch must be insulated to the full insulation value of the rest of the attic, the full R value. Now, it does not say that you have to put the same type of insulation on the attic access hatch. And indeed, if you're using a loose fill insulation, you cannot do that. The example shown in this slide is a very poor one. It shows a stay-fit bat which has been adhered to the back of this plywood access panel. And I ask you, how long will this last? Not very long when that is pushed out and handed down to somebody on a lower floor to lean against the wall and store it while you're up there rummaging around in the attic. So you as a contractor have to use your imagination in insulating the top of an access panel. And I would suggest that you think about a foam board insulation up there, something that will withstand some rough handling. But keep in mind that some foams are not fire rated, and they have to be protected from the interior space by some kind of a fire barrier, such as a half-inch drywall or a cement board adhered to the top of the plywood access panel. Mass walls, such as we've spoken before, log walls, ICFs, insulated concrete forms, concrete block and brick construction, have their own tables. And the tables say that you have to have at least half of the insulation in those mass walls on the outside or integral in the middle of the wall. And if you cannot do that, then you must refer to the tables for the standard wall construction. The special table for mass walls no longer applies. Steel frame buildings. There's a table for steel frame buildings. Some residential structures are built with steel frame. Basically, a steel frame building radiates heat to the outside just like fins on an air-cooled motorcycle engine, ferociously. And this table essentially says that they want a rigid, insulating, continuous sheathing over the outside of the steel frame studs and rafters to stop this thermal transfer effect. Insulation installed in floors over unheated spaces, such as unheated basements or crawl spaces, or maybe a bedroom floor over an unheated garage, or an overhang where a first floor overhangs the foundation. We have to have insulation installed between the joists in permanent contact with the subfloor, pushed up tight, in other words. And this particular slide shows a very poor installation of that insulation between the floor joists over an unheated crawl space. This crawl space, you'll notice, has some block vents to the outside. It allows outside air to flow through and ventilate that crawl space summer and winter. In the wintertime, that's cold. And that's why we put the insulation between the joists. Now, the picture in this slide shows a very poor installation, and I would suggest that you try to improve on that. Notice these are probably 2x10 joists, that's most common. And notice how thin it is between some of those joists. That's certainly not R30. And it's installed without any supports. If that's a stay-fit bat, it probably will slip down over time. So pay attention to the quality of your installation. Now notice also in this photograph the vapor barrier on the bare dirt floor in the crawl space. That vapor barrier has to be what's called a Class 1 vapor barrier. Basement walls can be insulated either on the inside or the outside. If they're insulated on the outside, they have to be insulated from the top of the wall down to 10 feet or the footing, whichever is less. Now, you may have a basement deeper than 10 feet. in some special situations. You say you only have to go down to 10 feet. Now, if you install the insulation on the exterior, you have to protect it from the weather. Sunlight destroys insulation. You have to protect it from physical damage, such as lawnmowers and string trimmers, and that protection must extend 6 inches below the grade. Here's an example of an exterior insulated basement. The foundation backfill has not happened yet, so you have a good picture of it. It also appears that this has a brick ledge. They've not brought that insulation all the way up to the top of the wall, and it looks like it'll be installing brick at this point. The definition of a basement wall, which is constructed and insulated as a basement foundation wall, as opposed to an exterior wall, which is constructed and insulated as an exterior wall, is the 50% rule. If it's more than half below grade, it's a basement wall. If it's more than half above grade, it's an exterior wall. And this example, as a walkout basement, has the slab on grade insulation to be installed along the outside of that outside wall. And we have to insulate even more in a slab on grade floor if it's a heated slab. If you install hot water radiant heat in the slab, or you have underfloor air supply ductwork, you have to put an additional R5 in that slab. And here's 3 methods of installing insulation in a slab on grade floor. Keep in mind that this is probably very rare in residential construction, except where you have a walkout basement. And figure 2 shows the insulation on the outside, and you have to protect it from damage. It has to go from the top of the wall down to the footing. Figure 3 shows it on the inside. But notice we're now talking about the full thickness of insulation all the way. We don't just have a small thermal break like we used to do, a 1/2 inch gap filled with a asphalt mastic material. The full thickness of insulation, 2 inches or possibly 3 inches if you have a heated floor or you're in a northern climate zone. Or if you're in a northern climate zone and a heated floor, 4 inches of insulation has to be installed there. So you have the option of putting it, as in figure 3, vertically down to the footing, or as in figure 4, vertically to the slab and then horizontally under the slab. For you folks who are building both residential and commercial buildings, figure 4 is not allowed in commercial buildings. The 2 codes are different. The residential code is the International Energy Conservation Code as amended. The commercial code is the ASHRAE Standard 90.1. And the 2 codes have different requirements in insulation for this particular feature. What about installing stretched carpet on that walkout basement floor? Where do you put the tack strip? Well, it ends up being right on top of that insulation at the perimeter. So this is allowed. It is allowed to cut back the insulation at a 45-degree angle and allow the concrete to continue all the way out and almost touch the exterior wall. And there's a point where you could install the tack strip right on the hard concrete. But how do you install tack strip? Well, on a concrete floor, you might put it down with a ram set. If you tried that in this example, you'd break that little 45-degree tapered concrete right off. I'm told there is an adhesive that can be applied that cures quickly and is strong enough to withstand the tension of a stretched carpet. So in this instance, you would install the carpet tack strip with a glue, an adhesive. But you should make some kind of mention of this in the documents that you leave the homeowner, because typically you will leave an unfinished basement and the homeowner will go in and finish that at a later date. At that point, if the homeowner doesn't know about this insulation being under the slab, his carpet mechanic may start shooting down the tack strip with a ram set. And therein lies the problem. So whatever documentation you leave with the homeowner at the end of the project, let them know how this basement wall and floor is constructed at that perimeter. Crawl space walls. The first example that we showed a couple slides ago shows the insulation being installed in the floor over an unheated crawl space. This is another example of insulation being installed in the wall of a heated crawl space. Again, notice the vapor barrier over the dirt floor. Now, the building code requires you to ventilate a crawl space. So here's one Where you have no block vents allowing outside air in, you must now install grills and registers from the heating system that serves the house above. And also, if you put a horizontal furnace in the crawl space, you have to somehow protect this vapor barrier. People are going to be down servicing that furnace. They're going to be changing filters, working on the temperature controls. You have to protect that vapor barrier from being damaged. In this case, think about installing a lightweight concrete floor, only a couple inches thick. They call it a mud mat, in the area where you come down through the access opening and over to and around the furnace at the very least. The vapor retarder has to be a class 1, as it says, 1/10 of a perm or less, and this basically means a 6 mil polyethylene or thicker. And here's the requirement for ventilating the crawl space, as we mentioned earlier. And for the exterior insulation on a foundation, if you have a brick facing, you'll have a brick ledge, and the code says you need not insulate under the brick. Practically, you cannot. The weight of the brick would squash the insulation, so they say you don't need to put any there. The next section talks about sunrooms, and sunrooms are treated totally differently with requirements for R values and U values. A sunroom is defined as a space that has greater than 40% glazing, and many sunrooms are being installed as greenhouses where people may raise exotic flowers. If you do so, install a sunroom as an addition on an existing building. The wall that separates the existing building from the sunroom must be brought up to the requirements of the new energy code, in other words, at least R20. If the sunroom is heated, many are not, but if you want to put some heat out there, you can either put a separate furnace in the sunroom, or you can serve it as a separate zone from the furnace that heats the rest of the house. That means you have to install some kind of zone controls and thermostats in the different spaces. Now, if you have a ceiling in the sunroom, the R38 insulation requirement drops to R25. In the previous example, one of the pictures shows that there was no ceiling. It was a full glass ceiling, which would be called a skylight. The wall value, if you had any walls, are no longer required to be R20. It drops down to R13. You have to put an insulated door in the opening between the sunroom and the existing house. An interior door will not suffice. It has to be a thermally insulated door. The U factor for the windows no longer is 0.35, it goes up to 0.5. The U factor for the skylight, remember 0.6 now goes up to 0.75. So the sunrooms have totally different insulation requirements. Now we turn to windows, and the area weighted U factor comes into effect. This is the requirement for the U rating for windows. And what that means is windows in the center of the glass have 1 U factor. Around the edge of the glass, there's a second U value. Around the sash is a third U value, and the frame has yet a 4th U value. And you must average all of these different U values to obtain 1 average for the entire window. Now, keep in mind that a small window has very little glass surface in relation to the frame, and a large window has a great deal of glass surface in relation to the frame. So the size of the window impacts the average U value. Now, in a given home, you may have 10 windows that are identical, but you may also have 3 or 4 different styles of windows. Each one of those windows would have to have an area-weighted U value calculated separately for it. And again, it has to be certified by a computer simulation. So each type and each size of window would have a separate submission for the requirements, proving conformance with the energy code. There are 4 requirements from the National Fenestration Rating Council. Their standards 100, 200, 300, and 400 talk about the thermal performance, the solar heat gain requirements, the visible light transmittance, and the leakage rate. Only the first ones and the last ones are required in Michigan. Solar heat gain coefficient and visible light transmittance do not apply. If you're using any of the trade-off or performance methods for demonstrating compliance with the energy code, the U values for windows changes. The 0.35 from the prescriptive table 1 and 2 in the code in Chapter 4 becomes 0.48 if you're using any one of the alternative computer simulations. There's an exemption for windows and doors up to 15 square feet of unusual windows, such as a stained glass window as we picture here, or up to 24 square feet of a unusual door need not comply with the provisions of the Energy Code. Let's say you have an antique door you've purchased from a restoration company. An old door might not meet the thermal performance of the modern doors, and you're allowed up to 24 square feet in compliance with the new Energy Code. And here's an example of the sticker that you must leave on the window. As a contractor, you leave this on for the homeowner to remove after the final building inspection and certificate of occupancy is granted. And notice the 4 criteria from the 4 tests from the National Fenestration Rating Council are depicted on this certificate, this sticker. Every window has one of these, and only 2 of them apply: U-factor and air leakage rate. If you're a contractor doing total window replacement, and that's your entire occupation, that's all you do, your windows must comply. Even though it's an alteration, even though it's a very simple thing, taking out the old, putting in the new windows must meet the provisions of the new Energy Code. Section 402 now talks about the air leakage of the building. We talked about air leakage of the windows moments ago. Now we're looking at the entire building. And the new code gets very specific about leakage, reducing infiltration, reducing air changes. And they want you to look at places you possibly never thought of before, such as in a duplex home. What about the demising wall between the 2 dwelling units? If you have a bathroom on an outside wall and you have a tub or shower against the outside wall, what about behind the tub, behind the shower? All sorts of openings, all sorts of penetrations. And in the energycodes.gov website, we have some examples, some photographs, some drawings, some checklists, ideas, suggestions for you to think about on where you might find leakage. And here's an example of all sorts of places in a house that you should be thinking about. And where we used to stuff scrap insulation around a window in construction practices many years ago, now we're looking at installing expanding foam around those windows. And here's another photograph showing that same expanding foam sealing the gap around a plumbing vent pipe going up into the attic. And at the end of the project, you have to prove that you have sealed up the house, and you can do it by one of 2 methods. The new Energy Code says that a visual inspection can suffice. Now, this is up to the option of the local authority having jurisdiction. And they can come out and inspect the house. This has to occur at a time of intermediate construction before the interior finished surfaces are applied, so that you can see the insulation, you can see the sealing methods, you can see the vapor barrier and how it was installed. Now, that's a time-consuming operation. The inspector may tell you to employ someone, a certifier, to do this and certify that your house is sealed up tight. But another method, a blower door method, is done after the house is completed, and it is the proof of the pudding, so to speak. It demonstrates the actual leakage rate of the house as it was constructed. And the blower door is basically an extending aluminum frame. It telescopes to stretch a canvas panel across an outside door. And you'll notice that here's the door. It's been opened. The residential door is open to the interior. The gentleman has installed the blower door, and he's now putting in the blower itself in a circular opening in the bottom portion of the door. And this is an exhaust fan, variable speed, with air measuring devices built into it, little probes. And you can adjust the speed of the blower, and you can read out the air volume that's being exhausted through that blower in cubic feet per minute. And the new Energy Code says that you shall have a maximum of 7 air changes per hour in that house. But it's at a pressure, or rather a suction on the house, of 1 pound per square foot. Now that's a lot. That's extreme, and it's on all surfaces of the house, the walls, on all sides, and the roof. Now typically in a residential construction, a winter wind from the northwest will press on the north and west sides of the house and air will enter. But on the south and east sides of the house, air will exhaust. Half the roof will have pressure on it to allow air to come in. The other half on the opposite end will have suction to allow air to exhaust. This blower door test, in effect, doubles that. It places all surfaces of the walls and roof under 1 pound per square foot pressure. And they're saying a maximum of 7 air changes per hour. Well, how do you determine that? It's quite easy. You measure the length and the width and the height of the house. You multiply to find the volume of the house in cubic feet. The blower door readout is in cubic feet per minute. With a simple division, you can see that you want no more than 7 volumes of that house to go out that blower door every hour. And at 7 air changes per hour, it's quite easily met. If you pay attention to the details of sealing up the house during construction, you'll have no problems meeting the 7 air changes per hour. If the building official wants a visual inspection, here's some of the things that the inspector will be suggested to look at. The air barrier and the thermal barrier. Well, the thermal barrier is the insulation in the house. The air barrier would be the vapor barrier, the polyethylene sheet, the visqueen. Looking at the ceiling in the attic, actually going up there and looking. Walls, windows, doors, rim joists, floors, and lots of other places. Again, suggestions for the people doing a visual inspection. The next section in the code requires new wood-burning fireplaces shall have gasketed doors and outdoor combustion air. Well, there's many types of fireplaces. There are fireplace inserts. There are gas logs. There are corn burners. There are pellet burners. The code says new wood-burning fireplaces. So that means what it says. So if you have a fireplace with a gas log, it doesn't have to have a gasketed door and outdoor combustion air. But the principle of this section in the code is to reduce infiltration. When you run a fireplace, when you burn a fire, the combustion air has to come from somewhere. And in the standard historical construction, it comes from wherever it can. It comes from doors and windows and causes leakage and cold drafts in all the rooms of the house simply to provide combustion air for the fireplace. So they're saying put outdoor combustion air in there. That's easily done. Gasketing of the doors may be a more difficult situation. Custom doors manufactured for site-built masonry fireplaces, you may not be able to get gasketing on them. But the overall idea is to reduce infiltration, especially when the doors are closed, there's no fire, and the fireplace is cold. The fenestration air leakage, the 4th value of the NFRC test, test number 400, says that you shall have a maximum of 0.3 of a CFM per square foot for a sliding door and 0.5 CFM per square foot for a swinging door. However, site-built windows, skylights, and doors are exempt from the leakage test. If you have an architect wishing to have fancy doors, windows, and cabinets built on site, there's no way for those to be shipped to a factory and have a factory take responsibility for them. So the code says that they're exempt from the test. The next section talks about insulated ceiling rated fixtures. The National IECC code says that insulated ceiling fixtures must be installed in a manner that prevents infiltration. You have to caulk and seal around them. Michigan has amended that code to allow the use of non-insulated ceiling rated fixtures to be installed. Obviously, if you're putting these in lower floors that are not insulated, you don't have to worry about it. But if you're in the ceiling of the top floor and you're looking at penetrating the roof insulation, the ceiling insulation, then you have to install an insulated ceiling rated fixture. That means you can put insulation right tight up against the sheet metal fixture and not overheat anything. But Michigan says that if you install a box, a fire-rated box with the appropriate clearances over the top of the non-insulated ceiling-rated fixture, they will allow it. But you must seal and caulk that box to prevent infiltration, just as the code talks about for IC-rated fixtures. For furnaces, air conditioners, and water heaters, we defer to the federal laws. The efficiencies of furnaces are minimum 80% combustion efficiency for heating, 13 SEER for cooling, and for water heaters, a heating factor, as it's referred to, of 0.62. The MUEC mentions nothing about this. Section 403 of the Energy Code refers to mechanical equipment, and there are certain mandatory requirements. And here's the list of them: temperature controls, heat pumps, air supply and return ductwork, HVAC piping insulation, circulating hot water systems, ventilation, sizing equipment, multiple dwelling units, snow melting, and swimming pools. First of all, our thermostats. The old snap-acting two-position thermostats are no more. The code now requires that we install programmable thermostats where we can reset the temperature at night. Heat pumps. If you have an air-to-air heat pump, the code says that you must properly size the heat pump for air conditioning the building during the summer months. However, if that same size cannot heat the building adequately during the coldest winter months, you are allowed to install supplementary electric heat. Only as much as is required, however, no oversizing. It does also allow you to install electric defrost heat. An air-to-air heat pump has to be shut down every hour or two and the evaporator coil defrosted with an embedded electrical heater, and the code allows the use of that. Ductwork outside the building thermal envelope must be insulated. Supply ducts to an R8 insulation thickness, return ducts to an R6 insulation thickness. Building framing cavities can be used as return ducts. Remember, we pan across a couple of joist spaces to create a return duct in the basement? We can still do that. However, we cannot use building cavities as supply air ductwork. Here's an example of ductwork being installed above a ceiling, an insulated ceiling. It will be after the ceiling board is put in. And the lower picture is installed above a corridor below an insulated ceiling. I, as a professional engineer, would not design in this manner, however. Remember, the codes are minimum construction. They outline the worst building that you can legally build. Think for a moment about a building where you've constructed an R20 wall and an R38 insulated ceiling, and 7 times every hour you take the entire volume of air in that space and you run it up through an R8 or an R6 insulated duct in the attic. That totally defeats all of the effort and money you've put into insulating the rest of the building. So I, as a professional engineer, would recommend installing the ceiling insulation over the top of this ductwork in the attic. We must now seal ductwork where we never had to before. This photograph is an example of a mastic sealant applied to duct. It's not pretty, but it works well, and I recommend this. It seals tightly, hardens, glues the ductwork together. It's also possible to use tape to seal joints and seams in ductwork. The duct tape that we commonly purchase at the hardware store, the cloth duct tape, silver in color with an adhesive backing, you know from experience, will fall off of a surface. After a period of a year or two, this adhesive will cure and the tape will fall away. It is not a permanent seal for ductwork. There are aluminum foil tapes available. Some are reinforced even with a fiberglass thread. Aluminum foil tape is commonly used on air supply duct board. That's a rigid fiberglass board with an aluminum foil vapor barrier, and all the joints and the seams are sealed with an aluminum foil tape, commonly not reinforced. However, I have seen instances where the aluminum foil tape will not even last a year. Its adhesive will cure and the tape will fall away. So be very careful about what kind of tape that you choose to seal up ductwork. Now we come to piping, referring to hydronic heating piping. Piping carrying fluids above 105 degrees, which would be hot water heating. Typically we would see temperatures of 160 to 180 in the wintertime. Or chilled water and refrigeration piping below 55 degrees must be insulated to a minimum of R3. And as we know, fiberglass insulation has an R value of 3 per inch. So this is equivalent to 1 inch of fiberglass or the equivalent foam plastic insulation. The exception is domestic hot water systems. They're not required to have any insulation on the hot water that you supply to the faucets in your bathrooms. with the exception if you have a recirculating hot water system. Then the entire supply and return system must be insulated to the value of R2, or 2/3 of an inch of fiberglass. We're also allowed near boilers to not insulate the pipe up to 4 feet away from the boiler, where you would have valves, pressure relief valves, unions, all sorts of fittings that would be difficult to insulate. So the code says that you can not insulate the piping for a distance of up to 4 feet away from a boiler or a chilled water coil or a heating coil if it's difficult to do so with all of the valves in place. Please do not insulate unions. Pipe unions must be left exposed for the service person, so in no case do you insulate the union. Any duct penetration through a building wall has to have a damper on it. The damper can be gravity operated or mechanically operated, but it must seal tight in the closed position, and some leakage rates are specified in the code. The exception to this are the combustion air intake and flue exhaust duct or pipes for furnaces or water heaters. You must not close those off. Equipment must be sized in accordance with some kind of a calculation program. The heating and air conditioning equipment is required to be sized properly so that the building does not have an oversized furnace or an undersized air conditioner. And one example is ACA Manual J, Air Conditioning and Contractors Association Manual J, which is based on the ASHRAE methods for calculating heating and cooling loads. Snow melting systems. The code says that if the pavement temperature is above 50 degrees and the outdoor temperature is above 40 degrees and it's not snowing, shut it off. Only when it's cold and snowing. So we have to have some sensors, not only temperature sensors, but moisture sensors, to shut off the snow melting systems when they're not required. Swimming pools have to have an energy conserving cover, a pool blanket. There are some additional requirements. The pool heater cannot have a standing pilot light. The pool heater has to have a time switch, basically to shut it off in hours of unoccupied or no use. And there has to be a switch accessible to the occupants, so that if you happen to be the last person leaving the pool, nobody around during normal hours, you can go over and shut it off. It's also exempt, you don't have to, if you have swimming pool heat supplied from solar or some other source that doesn't use fossil energy. Now we talk about this term called efficacy. We've mentioned it a couple times before. What is it? Well, it's defined back in Chapter 2, and it basically means efficiency. However, efficiency varies with the wattage of the lamp. Small lamps are less efficient, large lamps are more efficient, and the code recognizes that and approves it. And the lamps also have to be T8 or smaller in diameter. The designation of a fluorescent lamp, the number means the diameter of the tube in eighths of an inch. The fluorescent tubes that we've had for decades have been T12s. That means 12/8 of an inch or 1.5 inches in diameter. T8 means they're 1 inch in diameter. So the new energy code requires that we use high efficiency lamps, high efficacy at the various sizes, in the T8 style. Now, the lumens per watt, this is the amount of light that the lamp puts out for every watt of power input. At the 60 lumens per watt at the 40 watt lamps and larger is typical of normal fluorescent lights. However, to get that, you have to calculate the ballast along with the lamp. Now, it used to be that magnetic ballasts used 20% more energy in addition to the light. So a 40 watt lamp would use 8 additional watts in the ballast. We'd lose that heat. It'd go off into the air conditioning system. The new code limitation of efficacy says that at 40 watts, 60 lumens, that's all you're allowed. If you were to have a magnetic ballast, you would be dropping that efficiency down. So you must use an electronic ballast in order to obtain this efficiency. The maximum output for fluorescent lamps at this time is about 100 lumens per watt, and that occurs in T5 lamps that are designated as high output, or HO. And light emitting diodes are approximately the same efficiency as fluorescent lights. The current light emitting diodes, however, on the market go up to about 120 lumens per watt, Now, Section 405 talks about another method of complying with the energy code. So far, we've been talking about the prescriptive method. Section 405 talks about a simulated performance alternative. This requires a computer program. And it also requires the input of the fuel costs that are current in your locale. And basically what you do is you input all of the sizes of the walls and windows, the size of the roof, all of the thermal envelope criteria, the lighting watts and efficiencies, the air conditioning and heating appliance efficiencies into a computer program. And you input the cost of the heating energy in dollars per therm and the cost of the electrical energy in cents per kilowatt hour. And for the climate, the actual climate zone in which the house is going to be built, you run a simulation. And this is called the proposed house, what you're proposing to build. And the simulation will tell you how many dollars per year it estimates it will cost to heat and cool that house. Then you make a copy of that program, and you change the R values and the U values to the minimums that are specified in the energy code, and you run the simulation again. And you compare the two. And the simulated performance alternative says that you must improve on the performance of the baseline building, the one built to the minimums of the code, by a certain percentage in order to comply with the new energy code. This is one of the performance alternatives. In 2009, Congress passed what's known as the American Recovery and Reinvestment Act. Funding under that act has developed the codes as we now have them. Also under that act, we are required to report back to Congress 90% compliance within 8 years, which means 2017. And so as a result, we anticipate that inspection will become more rigorous. We will be doing more things, developing more submittal data, and there will be such as more insulation inspections, intermediate inspections rather than the original ones that we had, simply the footing inspection, the rough-in inspections for all the various trades, and final inspection. There'll be more intermediate inspections either by the inspector or by someone hired by the contractor to certify the condition of the building. This concludes our presentation of the Michigan Residential Energy Code.